So, good evening, everyone. I welcome you all to the last week and last session for this problem solving session of Analog Electronic Circuits course. In today's session, we'll be talking about the circuits mostly based on regulators, voltage regulators, and those type of circuits. So, without any further ado, let's quickly start with the problems. So this is the first problem that we are going to solve today. And in this problem, so this is basically a circuit given for getting a clean supply from a dirty power supply. So basically it is a voltage stabilizer circuit. And as we all use stabilizers, right? Currently, the devices or appliances that we are using, they already have inbuilt regulator in them. But earlier, people used to buy separate regulators for, let's say, fridges and all. They used to use those regulators for the fridges so that if there is certain fluctuation in your power supply, that fluctuation will not hinder your or will not damage your system or circuit. So this is a similar type of regulator circuit. In this is a Zener diode. And what is the property of a Zener diode? Like if somebody may recall, like what is basic property of a Zener diode? If you may answer, like what do you like? What is it that comes to mind when we say Zener diode? No answers. So basically, a Zener diode, it provides constant voltage for any range of current. And especially if we talk about it as high currents. Because if we talk about the IV characteristics of a Zener diode, so what happens, first of all, you operate your Zener diode in reverse bias. So it starts with a very low voltage, then it breaks down. And it breaks down at this voltage of, let's say, V Vx. Okay, at Vx it breaks down. So what happens? It is actually a very sharp breakdown over here. So it is somewhat like this, very sharp. So after this particular voltage, your voltage across the Zener diode never increases. So that's why it is said, like no matter how high current you push through your diode, your voltage remains fixed. That voltage cannot be changed. So that's why the output across a Zener diode is always fixed. So that's why these Zener diodes are used for voltage regulation. Okay. So now coming back to this question, in this question it says the circuit below is a conceptual schematic of a voltage regulator, as I mentioned. A dirty supply with ripples and noises is regulated into a clean supply with the help of this feedback circuit. So assume the op-amp has a gain of 1319, R1 has a gain of 19 kilo ohms, and R1 has a value of 19 kilo ohms, R2 is 23 kilo ohms. Now assume that the op-amp has a output resistance, that is R0, of 399 kilo ohms. Now with these values, what is the output resistance of the complete voltage regulator circuit. So what is the output resistance of this complete voltage regulator circuit that we have to find out? So first of all, like if we take this circuit, so in this circuit, here your op amp also has a resistor, right? R0, and that R0 is basically between that output node to let's say ground. Okay. So now first thing, this is like, if how do we find output resistance, or like if we want to find a impedance at a particular node, how do we find it? So the basic idea is, if you take a voltage source Vx and it provides us current Ix, then the resistance, let's say Zx, is Vx upon Ix. Correct? This is the resistance that you will get, which would be seen at this particular node. Now, if you see, the current is Ix, right? Now, how will there be any current distribution, or the how the current will be distributed at this particular node V naught? What will happen at V naught? What will happen at V naught? See, V naught has two branches, right? Like one branch is this, which is through resistors. So here there will be a current I1 and there is a current I2. So there are two current components, I1 and I2. Now, because of these current components, the Ix will be I1 plus I2. Okay. Now, we know that this particular diode, yes, this particular Zener diode will give a fixed voltage. Let's call it a reference voltage, Vref. Okay. So if at this node it is Vref, then the output at this particular node will be how much? It will be gain times of Vref, right? And the gain is, since it is negative feedback, like in non-inverting configuration, so V naught will be Vref 1 plus R2 by R1. Correct? So this is what the value of Vref that we'll get at this particular point. At this particular point, at this node, now here we already said that Vx is being applied. So at this node it is Vx. So at this node, the node voltage will be R1 upon R1 plus R2 into Vx. Right? And if we see, like, what is the difference between these two, Vd. So yeah, considering that only this voltage is working, so that Vd is minus of, because the potential is appearing at the negative terminal, and Vd is always V plus minus V minus. So considering V plus has zero potential and V minus has a potential of Vx R1 upon R1 plus R2 is Vd. Right? Now we know Okay, so we found out that VD is this much. We also know that in case of an op amp, V naught is A times of VD, correct? Gain times of VD. So our V naught will be minus A naught, or like A, where A naught is already given, which was 1 3, how much? 19, yes, 1319, right? Volt by volt. So minus A naught R1 upon R1 plus R2 into Vx. Now, if we see this V naught is actually the potential which is appearing at this node due to this op amp, like at this particular node. And there is a R naught. So the current I2 is actually V naught upon R naught, correct? So V naught we already know. So we can simply write it like A naught R1 plus R2 Vx upon R naught. Now this is I2, like the magnitude of I2. This is one part. Now second part is, here at this particular node it is already Vx. There won't be any current flowing through this to the input of the op amp. So the current I1 is actually Vx upon R1 plus R2. So these are the two currents. Now, as we mentioned that Ix is I1 plus I2. So we'll simply add I1 and I2. So Ix equal to A naught R1 upon R1 plus R2 into R naught Vx plus Vx upon R1 plus R2. So Ix is A naught R1 plus R naught upon R1 plus R2 into R naught into Vx. Zx is Vx upon Ix. So it will be R1 plus R2 into R naught upon A naught R1 plus R naught. Now, if we observe very carefully, this A naught R1 is much greater than R naught, correct? Because it is 1319 into R1 was 19 kilo ohms. This is much greater than 399K, correct? So what we can do, we can like neglect this R naught and we can write it like R1 plus R2 into R naught upon A naught R1. So the factor, actually this factor of R1 upon R1 plus R2 is known as beta. So if we want to write this Zx, we can write it as R naught upon A into beta. So basically what has happened, because of this extra additional feedback, your output impedance has reduced by A to beta times. Earlier it was only R naught. Now because of this feedback, it has reduced to A into beta. And now simply substituting the values, So we have 399K into here we can write it as 23 by 19 upon 1319. So the value turns out to be 658.21 ohms. So this is the value of Z out that we get for this particular circuit. Now coming to the next problem. So in this problem, it was given for the same circuit. In the circuit above, assume that if there is a ripple on the dirty power supply, the op-amp output allows the ripple through the through with a gain of minus 29 dB. So 29 decibels, and this gain is called the power supply gain. And assume that the voltage across the Zener diode is a constant and does not change even with a ripple on the power supply voltage. What is the power supply gain of the complete regulator circuit? So this power supply gain is this power supply gain. Let's write it as, like, let's say it is G naught. So the power supply gain was G naught, which was like 29 decibels. Now, if we convert into volt by volt, so this comes out to be 0.0355. Okay, so this is the gain. Now, as I mentioned earlier, like we have seen already for Z out, that Z out reduces by a factor of A beta. Similarly, after negative feedback, the gain of the circuit also reduces by the factor of A into beta. So the new gain G will be G naught upon A into beta, which is G naught 1 plus R2 upon R1 into A. So that is 0.0355 into 1 plus 23 by 19 upon 1319. So the new gain G is 0.000595. So this is the new gain that we are getting in volt by volt. And when we convert it into dB with 20 log of G, we get it as minus 84.515 dBs. So this is the gain that we get after negative feedback. So basically the thing that needs to be kept in mind is that the gain reduces with the increase with the negative feedback. So the gain and output impedance reduces with the negative feedback. Now next question. I don't know. Yes. So in this particular circuit, in the circuit given below, the inductor and capacitor are so large that the current through the inductor is constant and the voltage across the capacitor is constant. The MOS device has to be in saturation at all times, and Vg is Vt plus Vgst volts, and Vgst is 0.15. Power supply VDD is 1.9 volts, R is zero point 0.9 kilo ohms, and Vg is Vt plus 0.15 volts. Okay. So what is the maximum amplitude of Vd such that the device is in saturation. So the question is, your value of VD, or if we say it is VDS, correct? Because with respect to ground, if we are saying, what can be the maximum value that VD can attain so that our transistor always remains in saturation? So the condition for saturation is VDS should be greater than equal to VGS minus VT, correct? And here this VT is the threshold voltage, same as this VT. So this is threshold voltage. So your VDS should be always greater than equal to 0.15 volts. So the minimum VD value can be 0.15 volt for saturation. Now this is something that we know. Okay. We know that VDD is 1.9 volts. R is given as 0.9 kilo ohms, and the ID is fixed. The ID is this ID I'm talking about. Okay, the current coming from this supply. This is fixed. So ID is constant. Now, if the drop across this VDS is 0.15, we know that minimum VDS is 0.15 volt. VDD is like, if we say this is point VD, right? So there can be drop across this inductor and then VDS. So let's say Vx. So VD is distributed between Vx plus VDS. So we have, if we find this point potential VD, then we can say this can be the potential of our drain node. So Vx will be VDD minus VDS. So Vx is 1.9 minus 0.15 volts. So Vx is 1.75 volts. So this is the maximum Vx that can be there. Like this particular node can have a max of 1.75 volts. This is the maximum value. Because if the drop VDS increases, that means that potential across that point will also like change. So this is the maximum that we can get. Now moving on to the next problem. While the amplitude of VD is maximum, so VD is maximum 1.75. Yeah, VD is 1.75. What is the maximum amplitude of ID such that the device is always on? Which ID? Okay, small ID. This ID is being talked about. So this is the ID we are looking for. So that ID can be given by VD upon R. So VD is 1.75 volts and R is 0.9 kilo ohms. So ID turns out to be 1.944 milliamperes. Moving on to the next problem. So in this problem, again that small current, I'll take the snippet. Okay, so for this circuit, it is said that let ID is equal to Gm into Vj, and even for large amplitudes, what is the required Gn such that maximum ID is achieved when the amplitude of Vd is maximum? So Gn is given by 2 ID upon V overdrive voltage. Small ID maximum, we already found out it was 1.944 milliamperes. Okay. And V overdrive is 0.15 volts. So GM is 2 into 1.944 upon 0.15. So the GM, this ID, yes. So GM is 25.926 millisiemens. This is the value of GM that we obtain. Now in this question, if the ID of the given transistor, this is the transistor current ID, is given by K VGS minus VT whole square, what is the corresponding value of K required for the device? So ID is 1.944 milliamperes. This is the ID. V overdrive is 0.15. So the value of K is ID upon V overdrive ka whole square. So the K turns out to be 86.4 millisiemens per volt. And coming to the next question. So efficiency of power amplifier, which power amplifier? Okay, I guess I missed the circuit. This is some other question. So yeah, we'll stop over here. So these are the problems that we have for today. Now, if you have any doubts, we can take up the doubts. That's why I've prepared like very less number of questions today. So, do you have any doubts while preparing for exam? You can unmute and answer, like if you have any doubts in any like sessions or any question, any concept that is not clear. Yes. You, yeah. Any doubts?
Ma'am, for calculation of transfer function
Yes.
uh, for poles and zeros,
Yes.
ma'am, see, you said the poles are 1 upon RC.
Pole is yes, 1 upon RC, correct.
So I have two poles, say R1, C1, which having the
Yes.
values of R1, C1, and pole 2 is having the values of R2, C2.
Okay.
Now, ma'am, for calculation of the pole transfer function, I have to multiply them. What I have to do exactly?
Oh, okay. So the thing is, only by knowing the poles can you find the transfer function. So that is the question, right?
Yeah,
So it depends on the type of transfer function. Now, see, like let's say transfer functions, right? So if your system only consists of poles,
yeah,
your system is, let's say, you already know it only has two poles.
yeah,
Okay. So two pole system. Then how to write your transfer function? So the transfer function simply will be T of S or H of S will be 1 upon 1 plus S by omega P1, 1 plus S by omega P2. Okay.
yeah.
So this will give you the transfer function with DC gain of 1.
Okay.
Correct?
Yeah,
Now let's say if you have, this is for DC gain equal to 1.
mm,
Now for a DC gain of A naught, which is already given, like there is a DC gain of A naught, then how it be the transfer function? It will be A naught 1 plus S upon omega P1, 1 plus S upon omega P2. So this is how you can write the transfer function. And similarly, let's say from a Bode plot only, you found out your system to be like two zeros, three pole system with DC gain equal to A naught. Let's say this is the system that you found out from your Bode plot. Now,
yeah,
if you want to write the transfer function, how can we write? It is H of S A naught for the DC gain, 1 plus S upon omega Z1, 1 plus S upon omega Z2 by 1 plus S upon omega P1, 1 plus S by omega P2, 1 plus S by omega P3. So in this way, we can simply write the transfer function with the knowledge of poles and zeros. But this is easier when you have like Bode plot uh, thing. So from there you can write the transfer function easily. But if you are saying like if you want to write this type of transfer function from circuit, given circuit, it will be a little difficult. Why? I'll tell you. Because when we say, okay, at any particular AC node, the pole is 1 upon RC, the thing is, it is not actually 1 upon RC. The actual value is a little different, but it is close by. So 1 upon RC is not the exact value, but it will give you the desired result. But when you have like fix, you know the values of poles and zeros, like exact values of poles and zeros, so you can directly write the transfer function like this. There also you can write it, but it will not be like the exact transfer function, but you can say like it will be an approximate one.
mm,
Yeah. But from Bode plot, you can write an exact transfer function because you know the exact values of poles and zeros. There you are finding approximate values when we do 1 upon R. We are
ma'am.
finding.
Sorry,
Yes.
ma'am. By drawing a Bode plot,
Yes.
suppose first you encounter the pole first. In
Yes.
front of a DC gain, DC gain, you start with the DC gain, say
Yes.
about 40 dB. Start with the 40 dB, and
Okay.
then you encounter first pole.
No, so you are saying the starting you are getting like there is a pole and you are getting
On the
it.
gain side, I have 40 dB, say, on the y-axis,
Okay,
or
maybe I'll.
80 dB. Whatever values are not important. I just want to get myself clear on certain subject matter.
So let's say it is like 40 dB and this is gain plot. So what are
Yeah,
you trying to say?
yeah, that's right.
This is 40 dB. So
Yeah.
what you want me to do?
Now, first, it is having the DC gain, and
Okay.
at the first, you know, first decade, I go, I continue for 40 dB, and then subsequently I encountered first pole,
Okay. It will
which is
decay by minus
minus,
20
which
dB.
is minus 20 dB per decade.
Correct.
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 Now I encounter first zero.
Okay.
Now first zero, so I have
Yeah.
to.
So
It should be plus 20 dB per DC per decade. Correct.
no, no. So what will happen? See, here in a zero introduces plus 20 dB per decade slope. A
Yeah.
pole introduces minus 20 dB per decade slope.
Correct.
Okay.
Yeah.
Now, in this case, now here the slope was already zero. So you introduced minus 20 dB per decade.
Yeah. Yeah.
Now,
Yeah.
when you are encountering a zero can give you plus 20 dB per decade slope,
Correct.
right?
Yeah. Correct.
But you already had a minus 20 dB per decade slope coming, right?
Okay.
So that minus 20 dB per decade will be cancelled by the plus 20 dB per decade of the zero. That's why you
Okay.
will get a resultant of 0 dB per decade at this particular point.
Suppose if I encounter
Hmm.
next zero, so
Yes.
now I have to plus dB per decade. No, ma'am.
Yes. So it will be plus 20 dB per decade again
Okay.
because of this zero.
Suppose other way around,
Hmm.
ma'am. If I encounter first instead of first pole, I encounter first zero.
Yes.
So it will go first. Suppose I'm just hypothetically, ma'am.
Yeah, yeah. No, it can be possible. It is possible. So it will go like plus 20 dB per decade.
Now after first dB sec, I encounter the first pole.
Okay.
So shall I?
So
It will be flat one or how it will be?
it will be again flat, right? Because
Flat one.
plus
Okay. Parallel
20
to x-axis.
and then minus 20. So it will be again 0 dB per decade. Plus
Okay.
20 minus 20 will cancel each other.
Okay.
So that's why 0 dB per decade.
Okay. Suppose if I encounter another first zero, sorry,
Zero.
second, third zero, see
Okay.
third zero, then I have to
Okay.
go further up on 20 dB
Matlab
per
second
plus
zero. So it will be plus 20 dB.
dB.
Is it clear?
Yeah, ma'am. Thank you.
Yeah. So we have to basically in Bode plot, the plot that you represent, it finally represents the effective value of slope.
Yeah.
So here it is the effectively it will be 0 because plus 20 nullified by minus 20. So that's why it is 0. So you will report the effective values. Yeah, it is a very big mistake. Like it is actually a silly mistake, but people do make mistakes like this. So what we do, okay, we have in mind, let's say there will be two poles appearing at a point. So we know it will introduce minus 40 dB per decade. So what we do, let's say we already had like 20 dB per decade slope coming, plus 20 dB per decade slope coming. So from there, people start drawing it like minus 40 dB slopes. So, but what will be the actual result? Actual result will be minus 20 dBs, right? Because
Yeah.
plus 20 and minus 40 ka resultant will be
Yeah.
minus 20.
Yeah.
So that resultant has to be drawn in the Bode plot. So that is something that needs to be kept in mind.
Okay.
We always have to get the resultants first.
Yeah.
Okay. Any other doubts?
Ma'am, while calculating the output impedance,
Yes.
which is nowadays, I mean, is very common. So you
Yes,
have to
yes.
short, I mean, ground all the voltage power supplies, correct?
Uh,
Maybe on bias side, and the DC voltages are all grounded, and then you have to apply a small voltage Vx test voltage at the
yes.
output node.
So what we say is, see, for an op-amp, like op-amp will need a power supply, right? You cannot
Yeah. VDA.
turn that off. So
That's
power
right.
supply cannot be turned
Yeah,
off.
it's a power. Yeah.
But let's say the input signals or input supplies can be turned off.
Yeah.
And only one source will be there, and that particular source is the test source that we are applying at the output.
Okay.
Yes. So in lab also, when if you are performing output impedance analysis, so you'll use a test source, and you will give your VDD and ground rail to your like op amp,
Yeah.
but its input, whatever input sources are there, no, those sources will not be provided. Rather, they'll be
Okay.
open or grounded, depending on how they are connected.
Mm-hmm.
And the test source, say, you will get the voltage and current. You'll divide that voltage by current to get the impedance.
Okay.
Yes.
Ma'am, I was told while going through the lectures, the
Okay.
RC, this integrator circuit
Okay.
in the what you call as the op amp.
Yes. Yes.
Basically, this doesn't really gives because of there is no negative feedback in this. So circuit, this became a part of a bigger circuit where you should have. It's told. I mean, I was told. I'm told I followed the lectures. So in which they were told that this circuit by itself
Hmm.
won't be an ideal circuit because it don't have negative feedback, because it can be a part of the circuit. I mean, can be part of there is be some prior to this there are some say some circuits, op-amp circuits where you have RC network, I mean indicator network or gain one unity gain circuits and all. And that feedback has to come back because otherwise the circuit won't work as an integrator. Even theoretically, it is said it is that is it. It is something has been told. Circuit by itself,
Uh,
because DC operating point is not established.
okay.
It can be a part of the bigger circuit where you have a feedback coming out. Because here there is no feedback.
So here, actually, it is not true that there is no feedback. Like this capacitor is connected in feedback, right?
Yeah.
But the thing is, this is known as an ideal integrator.
Hmm.
So what will happen is, let's say your the impedance offered by an capacitor is
The
1 by
1.25
omega,
FC. Yeah. Yeah.
right? So if your omega is like, let's say 0 or very small, or let's say it is DC. So what will happen? Your XC will be infinite.
Infinity. Yeah.
So
Infinity.
basically, it will be an open circuit system,
Yeah.
right?
Yeah.
So the resultant circuit will somewhat appear like this, correct?
Yeah. Yeah.
So now what happens? This circuit is actually an comparator.
Hmm.
So
Hmm.
it will give you saturated outputs. So rather than behaving as an integrator, it starts behaving as a comparator.
Okay.
So what people have done to overcome this problem is they designed a practical integrator. So a resistor was introduced in parallel to this capacitor,
Hmm.
so that
That will
for,
accept the feedback.
yeah, so that this condition never comes into picture. Like
Hmm.
let's say if omega is 0, then too your resultant over here will be r. So this z parallel will be r parallel to c, and z parallel will be r for omega equal to 0 or dc, right? So it will still work with a negative feedback rather than becoming a comparator. So it's somehow stabilizes the circuit, and this is known as practical integrator. This is practical integrator. Whereas the earlier one was ideal integrator, that is ideally not used because of these particular issues. So practical integrators are used in the circuits.
The problem you have solved some time back, is having the two-stage amplifiers, the
Okay.
cascaded one in a cascaded version. The
Okay.
output of the one is fed to the input of
Yes.
the other, so that
Yes.
it gains get not cascaded, madam, cascaded.
No, no.
Yeah,
So if the output is getting fed to the input of other,
other,
then the
yeah,
cascade.
yeah,
Yes, this is the configuration, right?
yeah.
Yes.
Now, in this case, ma'am, the gain of the one and RD of the rather GM and RD of the first one get multiplied with the GM and RD of the second to give final
Yeah, yeah.
gain.
So final gain that you get is like GM1, GM2, RD1, RD2.
Yeah,
So in this, the resultant gain, G resultant is approximately equal to GM1, GM2, GM1, GM,
RD1, RD2,
RD1, RD2.
RD2.
Yes.
Yeah,
But this is the same case even for Cascode as well.
cascade as well. Okay, okay,
Yes.
okay, okay.
Cascode also like similar results. Like gain me, you don't see the difference. The
Now,
difference majorly comes in terms of your output impedance in both the
okay.
cases and
Now,
both.
ma'am, if I want to calculate the output impedance
Yes.
of this circuit, now
Okay.
looking at from the output side,
Yes.
now, ma'am, how do I calculate it precisely? Because the calculate, I mean, the answer given is too lengthy, and I mean, it's too difficult to memorize. You cannot really, I mean, learn it by heart. You have to derive it, or come to some point where you can able to find some solution to this.
Mm-hmm.
Say you have RD1, RD2,
Hmm.
GM1, GM2. You
Hmm.
have C1, 2 in between the input and output side. Output of the first one, and then you are have C1 on the output of the first and C2 on output of the second, and then you are applying the Miller's theorem, and distributing them between the two nodes. I mean, input and output. Then
Mm.
which you are already done, ma'am, but I have little time.
So
That's the one that is C1 2, and the
yeah,
one
yeah.
which is on the input side. This is on this side. Output of the first one is C1. Output of the second one is C2.
Yes. So let's say this is a capacitor C1. This is
Yeah,
capacitor
that's right. C1
C1.
2. Yeah, yeah,
So, how did we solve it? So, this C2 will come here.
yeah. C2 is already there, and then C1 is already there on the input side. C2 is right. So you are, ma'am, you are rightly drawn. C2 is there on output side.
C2 will be here.
Yeah, and C1 is
And
between the two.
here
Yeah,
you
that's right.
will
That's right.
get C1 plus A times of C2.
Correct, correct, correct. Yeah, yeah,
Correct?
yeah, yeah.
Yeah.
Now
But,
this A, sorry, ma'am, A is the gain of the entire system. That GM1, GM2, RD1, RD2. The
this
gain,
A,
ma'am, again
this A
you,
you are talking about, right?
yeah, ma'am, yeah, ma'am.
So, this A, ideally speaking, this A should come from this one, like second stage. So this
Okay,
should be like A2. Why I'm saying this? Because like when you have a simple, let's say CS stage, single stage. So at this stage, you will again see a capacitor C. So here, the effective capacitance that you get is A times of C. This A is the gain coming from this particular stage, right?
okay.
जिसके इनपुट और आउटपुट के बीच में your capacitor is connected.
Correct, correct, ma'am. Correct, right,
So
right.
from that concept here also you should get A2, right?
That is GM2, RD2.
Yes.
Okay.
From this particular concept, if you relate it there, then
Yeah, 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 yeah. That's right. That's right.
that. Because if you think of it from that point also, like, okay, let's say you are getting V in over here.
Yeah,
Here you are getting A1 V in. Here you will get what? A1, A2, V in, right?
yeah.
So what is the actual effective gain that you are seeing between these two nodes? It is A2 only, no?
Yeah.
So A2 will come. Yeah.
Okay. Now this same circuit, ma'am, this RD1, I mean RD2, RD2 GM2, RD2 plus parallel to 1 upon GM2 parallel to C2 plus C12. They are all parallel to each other, ma'am. On output side, on the second stage, ma'am, on the C2 side, I mean the GM2 side, 1 upon GM2 is parallel to RD2
1
and
upon GM2.
huh, is parallel to RD2 is parallel to C2 1 upon C2 S. You can put it S into C2 plus
Oh,
what
so you are saying, okay, so at this point,
C2 plus
for
C12 S into C2 plus C12.
stage 2,
Stage 2, yeah, stage 2.
for stage 2, R will be
RD2 you can say whatever.
RD1 parallel RD2. Like RDN, I'll write better RDN, RDP, correct? These two
Yeah,
will come in
RD.
parallel.
Okay, your
Then,
circuit is slightly different.
par-
There is no this one on the top. It's only the ID over there on top. Is
oh,
ID.
okay.
You
So
have drawn.
rather than this, there is only RD.
Yeah, there's only ID, ma'am. Yes, ID2 rather.
Okay, so instead of this, here it will be RD. Then
Okay.
C2S, correct?
Yeah.
And
Plus
what else will come
C12S
into
also will
picture?
come, no, ma'am. 1 upon C1, C2S
C.
plus C12S, because that part also will get. The C2 is a circuit beds, and C12 also had a
No,
this one
no.
over there, no?
So what are we finding at the end? Aren't we finding only Z out?
Yeah, ma'am. Yeah,
So Z out is particular node pe we are seeing, right?
yeah.
So is particular node pe if we see, so this RD will come, 1 by GDN will come, this capacitor C2 will come. Other than that, will there be any other term coming into
GM2
picture?
won't 1 upon GM2 won't come in the picture.
1 upon GM2. I mean, are you considering like RD to be as 1 upon GM2 plus
ID2, yes, 1 upon G.
RD2? Are you considering it like this?
No, what I'm considering is GM2 itself, 1 upon GM2, and then RD2, that is the drain resistance at the MOSFET 2, second stage, plus C2 plus C12 into S, because C12 is going to be divided by the Miller's theorem, na, ma'am.
So that we are already considering, no? This C2.
As a C2, you consider that part also.
Yeah, here C2S is there, no? This is coming from this C2, which is the Miller capacitor.
Okay, you have considered that part of it. Okay,
Yeah.
okay, okay. Okay, then RDN.
And then there can be like another capacitor which is drain to body. So
Okay.
CDBS at stage 2.
Now, ma'am, tell me one thing. Correct
Huh.
me, rather. Correct me. GM2 won't come in the picture. 1 upon GM2 won't come in the picture, ma'am.
No, no. See, it depends. Like RD, generally we consider like drain resistance to be 1 upon, let's say if you say like 1 upon, is it 1 upon GM plus GD here? I am not. So, like RD is equivalent to 1 upon GDN. So that's why whenever we consider like drain resistor, we most of the time consider it as 1 upon GDN.
Okay, okay, now
But
that is okay, okay, okay. Sorry, I'm mistaken. Because
yeah,
RD, you are right in capital. So the RDN and DDN is same. I mean, 1 upon GDN. That's okay. That's right. That's okay. That's okay. And C2S, CDS2, okay. Okay. So that part you have to either you have to take RDN or 1 upon GDM. Correct, ma'am?
RDN, RDN is equal to 1 upon GDN.
GDM, yes, yes.
So they're like
Yeah,
interchangeably you can
I got
use
your point.
them.
Yeah, yeah.
But
RD is a capital
RD,
in
no,
capital
what
at
I'm
times.
saying is the value of RD, we approximately always consider it as 1
Yeah, yeah.
upon GDN,
Hmm.
but it is like mm, GM term also comes into picture, but we ignore that because GM, that 1 by GM term is very small
Okay.
compared to 1 by GDN term. So that's why we ignore that. So I guess RD is like drain resistance. I should write it like R drain.
Yeah, yeah.
It is. It turns out to be 1 upon GM plus 1 upon GDN. I'm not very sure. And what happens is this term is very small compared to this. So we ignore this and we see, okay, drain resistance is equal to 1 upon GDN.
Okay. That's the
So
internal one, correct?
internal one, yes.
So
This
that's
is
there where
internal.
at times it get confused because internal resistance RD, which is actually diode in the drain circuit. I mean, from the VDD to RD, and the drop across RD at times RD and small RDN gets this one. I'm slightly okay.
No, no, yeah. So that's why
Yeah, yeah, I
we
understood.
should be
Understood.
very particular
Yeah,
how
yeah,
we write it.
yeah,
So
yeah. Right.
whenever I write internal resistances, I make sure I use small letters.
Yeah, yeah. That's right.
And whenever I'm using a resistor proper, like external resistor, I make sure I'm using a capital letter with all the denotions. Because yeah,
RD, RS,
sometimes it
and all.
can
Yeah.
be confusing because RD, like if somebody is listening to it as a audio record, so it will be very difficult for that person to figure out whether that RD is the external resistance that I'm talking about or is it the drain resistance.
Yeah.
But small RD is actually the drain resistance, which we denote most of the times by 1 upon GDN. And capital RD is the external drain resistor that is used in the CS stage. So, yeah. So, those two need to be differentiated from one another. May I get out?
If I want to bring the poles closer to each other, hypothetically, ma'am,
Poles closer to
closer
each
to each other, they are at a quite distance. If I want to bring it closer, shall I add C1 to some resistances, capacities in series with C2, C12? Can I bring it closer to that so that entire value is reduced? Is it? I mean, It is
No, but why do you want to?
hypothetical. I'm saying that may not be a requirement. Suppose the two poles are wide apart,
Okay,
and
if they are
suppose I
wide
want to bring
apart,
it closer to little closer to each other. See,
okay.
then
So,
shall I?
see, what can be done is you cannot add something in series, right?
Okay.
Like if there is an internal circuit,
Mhm.
you cannot add anything in series to that
In
circuit,
internal circuit, yes, yes,
in
yes.
internal circuit. But you can, like always, you can add something in parallel to the circuit,
Okay, okay.
right?
Outside you can add it. Yeah.
Outside can be added in parallels.
Yes.
Now we know for capacitor, when you add things in parallel, what it actually does, it actually increases the capacitance.
Mhm.
Whereas when there is a resistor, the resistor, when it is added in parallel, it actually reduces the resistance.
Mm.
Correct?
Yeah,
And if
that's right.
we want to bring two poles closer, that means let's say we are reducing the value of pole for one, like we are reducing the value for one extreme pole to bring it closer. So what we are doing, we are actually increasing the no. So if we want to bring it closer or lesser, less के case में you will increase the value of resistance or capacitance because pole we know it is 1 by RC.
Yeah.
Now, if you want to, like, if it is a left side pole and you want to shift it to right, at that point, your R should be less and your C should be less. Getting my point? So, what I
Yeah.
mean
Yeah.
is, like, let's say you have two poles, okay? Now, one thing to bring closer, what you can do, one action is this, shifting this pole to other side. So, while shifting, here it is 1 upon RC is your pole. So to shift it this side, that means your 1 upon RC value should increase. That means your R or C should reduce. So
Yeah.
for the
Yeah.
1, your
It should
R
reduce.
should reduce or C
Or
should
C
reduce.
should reduce. Yeah. Correct. Yeah.
Reduction of C is not possible because you cannot add anything in series. So
Hmm.
what you can do, you can add parallel resistor.
Okay.
Correct?
Hmm.
Now second option is you can bring this one to this side.
Yeah.
For second option, pole remains 1 upon RC, but here you are reducing the value of 1 upon RC. That means you have to increase the value of R and C. So R should be increased, C should be increased.
Yeah.
Ideally, we know how can we increase the resistor by adding it in series.
Yeah.
But internal circuit mein you cannot add
Yeah. You
anything.
cannot do it. Yeah. I understand.
So that's why you will add a capacitor in parallel.
The C12 is a internal resistor, internal capacitors, madam. Correct.
Yes,
That's that's the point. Yeah. C12 is the internal
all
capacitors.
the capacitors, see, other than any capacitor which is said to be like a load capacitor,
Okay.
instead of
All
that,
inside.
any capacitors that we have analyzed which are terminal capacitors, those are internal capacitors that come
Okay.
because of the MOSFET operation.
Okay. Okay.
All capacitors are internal except the load capacitor, and if there is certain bypass capacitor in the input, that would be there.
Okay.
But in between the circuit, whatever the capacitors you see, they are internal capacitors.
Okay.
So you
The
cannot
coupling
put.
and yeah. Yeah. Okay.
Yeah. Any
Ma'am,
other?
what is the formula for Z? Zeros?
Uh, Zeros, I guess we discussed, right? It was
Maybe I
GM.
missed that lecture. I don't know.
Uh, I need to take out
Just give
that.
me initial this one. I can work at my
I
end.
guess if I'm not wrong, for zeros, it is GM upon C, like that Miller capacitor.
Okay.
If I'm not wrong, this is the value. But please check it once. We did discuss this while we were discussing the poles and zeros concepts. No, we
Okay.
discussed this, and yeah, it has GM in it, and definitely that Miller capacitor comes into picture. So most probably it should be GM upon C Miller. So
Yeah.
ultimately it is like 1 upon RC,
Mm-hmm.
correct? But yeah, please check this. Check this once. Uh, we have done this. I don't remember right now, but most probably it should be the case for zero. Yeah. Yes. Any other doubts?
Ma'am, but as you said that, the values are in between the two, this one poles. I mean, in between the two decades rather.
Which values I didn't get?
Poles and zeros, well, calculation of poles and zeros.
Okay.
So you have to calculate precise the value of that particular, this one, pole
Huh.
or frequency, pole or rather zero.
Huh.
Correct. So
Correct.
that you have to find out on the x-axis only. That is for the omega part of it.
Yeah, pole and zero ultimately means they are frequencies, right?
Yeah.
At what frequency your transfer function goes to zero, at what frequency your transfer function goes to infinity. So
Hmm.
that is the idea, that we introduce poles and zeros. So they are ultimately frequencies.
Hmm.
Yeah. Any other doubts?
Last week, ma'am, you have calculated, done that problem. Can you revert back to it? Is it possible?
Yeah, I
The
can
same
do it.
cascaded one. I just have one doubt about that. Last week's, ma'am. I think last Monday.
Yeah. We did cascode last time. Last time.
Cascaded and a cascade. It is basically solve the problem.
This one?
This one. I'm talking about this
Okay.
one only.
Okay.
Now, if you see, go to the second part of it. This is okay. Second part of this question, cascaded question to this.
That
I
was
mean,
cascade.
yeah, this is the one.
Okay, okay.
This is the one.
Compensation one. Yeah.
Yeah, this is the one in which you have calculated this transfer function, correct? Which is
Yes, yes, yes.
yeah. So now this function, you have all the values, even it is output impedance. They ask for the output impedance, if I'm not mistaken.
No, it was compensation capacitor value in this
Oh, that
problem.
is okay, okay.
Yeah. Compensation capacitor was asked, like the
Oh,
extra capacitor that
extra
we.
capacity you have put parallel to
Yes.
this. Yeah.
Yes. So that was the problem.
Okay.
Yeah. Hmm. Yeah. See this.
Yeah, this is the one which
Zero
I was
value,
thinking about.
it is gm upon cc by 1 minus gm upon rc.
Okay.
That is with this cc and rc coming in parallel. So this is the formula for zero. So ultimately zero is like gm by rc, gm by c. The resultant that you see is gm upon c. And it is also like 1 upon rc. In those terms
Hmm.
only you will get the values. Yeah. Maybe you can look into it, but this was like compensation capacitor value. Z out, हम लोग इसमें शायद we didn't calculate Z out in this. I don't know. Was it a week before? Z out. Is it okay? It is a single stage. In single stage, we did calculate Z out. Cascade, we did, I guess, but in which week I am not like very sure.
Ma'am, in
But
the case of cascaded say two-stage amplifier or
yes,
two-stage or three-stage, whatever is there. Now you
yes.
have to, when you asked about the output impedance, you have to
Okay.
consider impedance as the output only, correct? Or you have to consider that you have to trace it back. Did not be correct,
Uh,
because the equation what has been derived, it involves all the most of the parameters except GM1. That is, everything is involved.
Yeah, GM1 will definitely not come, but uh, mm,
Typically, output impedance, madam, we are referring to output only, not
yeah,
input
yeah,
side.
we are
Correct?
referring to output node only.
But then in the equation, some of the equations I found that it has some combination of C1, C2, this, that. I mean, it's a bit lengthy derivation.
Yeah, yeah, yeah. It's not that straightforward.
I mean, once we know, it doesn't matter. Once we know that this is parallel to this, or this is in series with this, or we have to
Yes.
consider input side of it, then it can be worked out. But once it is not clear, it will become too, too complicated at times.
Hmm.
Maybe I'm not able to represent. I'm not able to tell you the right this right words. But when you draw, when try to find out which are the components which are parallel to each other, or I mean basically current division or voltage division if they are
Yeah.
in series. So in that case, ma'am, it's like because output impedance is the output should be at output, but there are
Yes,
some
it is
elements
an output. But see, the thing is,
maybe having some cascading effect of input resulting into some output. I
no,
don't know.
no,
I mean
no.
that is something,
So,
ma'am.
if let's say, let's analyze this part only. Let's analyze this particular circuit only to get a little clarity, because that is not as straightforward as we are thinking. Okay. Now we have got to like second stage. We have two stages. There are certain voltages, like let's say यहाँ पे VA है, here you have VB, this is VDD. This is where you are applying your test voltage, correct? And
Yeah,
you have your IX. Now the point is, here there is a capacitor, which is the Miller capacitor, internal capacitor.
correct.
Now the thing is, this IX is flowing, okay? So this IX, how will this IX flow?
It will get divided, no, ma'am. It
So
is,
this IX will be flowing through this like op-amp
yeah,
I1. There will be another component which will be passing through this capacitor to I2, right?
yeah,
And this is an AC source.
yeah.
Since capacitor is working, that means it is an AC source. So now there is a current distribution, and that current is being distributed here, here. There will be another current which will
Yes.
be coming from this MOSFET, like I3. So if we write like IX, so how can we write it? We can write it as it is I1 plus I2 minus I3, considering the direction opposite,
Ix
right?
is equal to I1 plus I2, okay, minus.
Now, when we want to write, let's say Z out or ZX, ZX is ultimately Vx upon Ix, right?
Yeah,
So Ix has the component of I1. So this I1 will give rise to your GM2 term,
yeah.
right?
Hmm.
Now here this I2 is there. No, this I2 will also introduce certain components with it. Like this current, again, if we see how it flows, so it will flow like some part will come here, here, and since they are in series, and here also there is another capacitor, so another current over here, right? So this current will be further distributed. So like now
Hmm.
I2 is being distributed into, let's say, I5, I6, and I7. So here now your I2 is actually I6 plus I7 minus I5, right?
Yeah,
So I2 has further distributed.
yeah.
So now to find the value of I2, now you have to find I1, you have to find I2 and I3 to get your Ix.
Hmm.
Now while calculating your I2, you will see there will be components from this first stage coming into picture, right?
Hmm.
While calculating current I2. So
Hmm.
it makes sense that we are getting the components a first stage also, but it is not that straightforward.
Yeah.
Uh, as it can be done for a single stage, it is
Mm.
not that straightforward. Uh, I mean, you can definitely take approximations, like considering it to be very small and considering that you only have that single stage and doing the calculations.
Mm.
But it will be always an approximate result.
Yeah.
But
Okay.
when we are going for like exact results, so it makes sense that we are getting like first stage components, right? Because this current is being distributed, it is
Yeah.
going till the first stage.
Yeah.
So we should get that value as well. So yeah, that's why we are getting those components too.
Okay.
Yes. Any other doubts?
No.
There's another student. Vinod. Vinod, do you have any doubts? Vinod, are you there? I don't know. Okay, are there any doubts, any other concepts which are like not that clear? Else we can break over here.
Yeah.
And in any case, like if you feel any doubt, feel free to write to me, and we can sort it out together. If I'm unable to solve, I can take that problem to even my professors, like if it is something like that. But yeah, that's a. So thank you so much. Actually, I didn't expect thank you so much for being there today, because I know this session was actually rescheduled, right? Because I had my exams and I could not take that session. But thank you so much for being here. At least a single even a single student provides that boost key you want to teach. And so thank you so much for being there all the way. I guess you were there since the first session, right?
Yeah.
Thank you so much for.
Ma'am, thank you. Thanks a lot. Thanks a lot
It
for
was
your
nice
time,
interacting with
guidance,
you.
gratitude. We want to express your gratitude. Your time is very important. You have amplified our knowledge. It's like, we are carried out the endoscopy. You inserted that fiber optic inside the MOSFET and give us really more and more clear picture. It's difficult. It's a tricky, trivial subject. It has a complications, but
Yeah,
we
there
got
are.
a fairly good idea. It is complicated because it has a lot of parameters coming in. It has a lot
Yeah,
of
actually,
own
still,
cascading effects.
yeah, I haven't, like, I'm not currently working on analog circuits, but
Okay.
it's all thanks to my faculty personally, who has actually taught the subject really well. So that's where I get those insights from. So yeah, I would like to thank my professor. And other than that, when there are questions like from your side or others, so even I sometimes think, okay, what might be the reason? What could be the possible reason? So that also triggers to few things that we are seeing or some patterns. So yeah. But thank you so much. It was
Man, thank
nice
you, ma'am. Thank you.
interacting with
If you
you.
happen to know Mr. Chatterjee, please convey my regards to him. I referred his.
Uh, Professor Chatterjee, actually, I have never interacted with Professor
Okay,
Chatterjee.
okay.
So I was
He-
assigned this subject.
okay, okay,
But
okay.
yeah, so
He,
actually,
he-
this subject, Professor Nihar taught us in
okay,
IIT
okay,
Gandhinagar.
okay, okay.
So the insights that I bring in actually are from his, they are actually his insights. So all the bits and pieces that I
Yeah.
sometimes deliver, they are actually his insights. So
Mr. Chatterjee is just too good, too wonderful. I mean, I will appreciate his, and he gives example which are at times a little hilarious, but wonderful. I mean, he was too good. I mean, I can tell you that.
Okay.
I mean, I have referred his books. I haven't I referred his this one, his lectures
Lecture.
and his yeah. He's very good. I mean, very good. And I got some concepts which are, so I passed out long, long back. So I
Right.
just want to brush up my knowledge so that I can get tuned with what is the latest in the technology. The technology is moving
Right.
fast, and there is a tremendous gap between what I studied and now it is.
Now what is going on? Yeah, true. Even
Yes.
I did it last year, before last year.
Okay.
So this particular subject, when Professor Neha taught me, so
Okay.
he used to get like examples from research papers and all.
Okay.
So that's when we used to realize. But yeah, thank you so much for being
Thank you.
there till
Thank
the
you. Thanks to
last.
you and your team and everyone. And thanks to the government also giving us opportunity to learn. And thanks to
Yeah,
my all colleagues who have participate in this particular classes, because their questions also amplified my knowledge and add
yeah.
the new dimension to my knowledge. Thanks a lot. Thanks to all of you. God bless.
Thank you so much. So with this, we are finally concluding the sessions, and hope you have all the best wishes to people who are going to take exams, and have a wonderful evening ahead. And let's see if we cross paths again in some other subject, and where I could again be a TA for any course, and we can interact again and meet each other again. So, till then, see you all. Have a wonderful day, a wonderful evening ahead. All right. Bye. Good
Thank you.
morning.
Bye, man. Thank you.